get set up from the current slide. I don't know of any major announcements to make. I will say this. This class is one of the better classes I have about getting research papers in. It looks like 5 have been turned in out of a class of 17. So that's not quite a third, but getting close to it. But we're past midterm, so folks keep working on those papers. Or start working on them anyway. Okay, first test, I'm missing 2. Okay, so I need those. And second test, I've gotten 3, so keep working on those. We're in 5.3, so we're approaching the midpoint of Chapter 5, so the next test is not that far off. Other thing is, normally I have office hours tomorrow on Fridays on the Birmingham West campus from 8 to 12. Not tomorrow completely anyway. I have an eye appointment right across the street here at the UAB West Hospital. I thought it was going to be at Eye Foundation Hospital, but they said, no, he's at this one. I said, no, that's fine. It's right across the street from where I work. So I have that at 8:15 in the morning, which means if they can get me out of there by 9:15, which I'm not sure they can, then I should be back on the Birmingham West campus, hopefully before 10, but no guarantee of that. So I'm shooting for around 10, maybe a little earlier, but more likely a little later. But I should get there sometime before noon, because that's when I'm supposed to leave, though I usually don't leave that soon. All right. Any questions? All right. If not, let's get started and continue in Chapter 5, Analytic Trigonometry. 5.3 is solving trigonometric equations. And if you thought that whole mess about trig identities was just something, a good fun exercise to do, no, you are going to need to reduce expressions into simpler forms so that we can solve trig equations. That's the whole purpose. So here we'll use standard algebraic techniques. That means factoring, common denominators, whatever it is that is required to solve trigonometric equations. We'll solve trig equations of the quadratic type by factoring and solving each of the factors. We'll solve trigonometric equations involving multiple angles. That's a little bit different, but it carries on the same thing. And then, of course, we'll use inverse trigonometric functions to solve trigonometric equations. I don't think we've done any of those yet, have we? Inverse trig functions, or have we? I'm teaching so many different math courses. I know some of the courses, yeah, we do that all the time, but I couldn't remember if we had done it in here. All right, so let's introduce the section. Okay. To solve a trigonometric equation, now this is a conditional equation, not an identity. Okay, you'll use standard algebraic techniques when you can, okay, when possible, such as collecting like terms, factoring, putting things over common denominators, whatever it takes. Your preliminary goal in solving a trigonometric equation is to isolate first the trig function on one side, and then you'll go on trying to solve it from there. So this is a little different from regular algebra, where all you have is a variable. You isolate the variable, and that gives you the answer. Now we isolate the trig function first, and then we'll try to find an answer once it's isolated. Okay, for example, to solve this equation, very simple equation, 2x, I'm sorry, here we have Caitlin and Bree. All right, good deal. Okay, here's a pretty simple trig equation. 2 sine x is equal to 1. That's obviously not an identity. This is only going to be true for certain values. Okay? Here's Ariel. Okay. Now, how would you proceed to try to solve that? Divide both sides of the equation by 2. So wipe out the 2 there, make it 1/2, and you get sine x is equal to 1/2. Now, at this point, you start asking yourself, what values of x when you take the sine of it, will you get a value of 1/2? You want to think of any angles that when you take the sine of that angle, you get 1/2. Certainly 1/2 is within the range of sine. That's between -1 and 1, so that's good. Is there an angle that will give you that? Please say yes. Okay. What? Okay. Step 4 was a long time ago. Say again?
Sine of 30.
30 degrees or pi 6. Pi 6 or 30 degrees. Y'all knew that, didn't you? The sine of 30 or pi 6 was 1/2. I hope you remember that. Okay. Now, but that's not the only solution, is it? Okay? Because you see here, here's the graph of a sine curve. And it keeps on going and going and going and going in that direction too, forever. So you have a lot of places where the sine of x is equal to 30. That's going to be at pi 6. And then it'll also be pi 6 short of pi, because you see sine is positive in the first and second quadrant. So it'll be a 1/2 on the way down. So that'll be pi 6. You know, in other words, 30 or pi 6 will be your reference angle subtracted from pi. So there'll be 5 pi 6. And then once you have those two, every other one is just 2 pi away from it. So what we say is, here's the solutions. X is equal to pi 6, 5 pi 6 on the interval from 0 to 2 pi, which is right. No. There's pi, here's 2 pi. 0 to 2 pi. Those are the two places. But because it repeats itself, then it's going to be pi 6 plus 2 pi, or pi 6 minus 2 pi, or pi 6 plus 4 pi, or minus 4 pi, or 5 pi 6 plus 2 pi, minus 2 pi, plus 4 pi, plus 6. Yeah, it keeps going forever and ever. So there's a shorthand way to write that. If they don't give you an interval, like saying from 0 to 2 pi, if it's 0 to 2 pi, you found them right there, okay? If it's beyond that, if they don't give you an interval, I have to get my pen adjusted, then we mark Christian here, okay? Anyone else come in since I called roll? Okay. Now, so how do we write this? X equal pi 6 plus 2n pi. Now, they put the n in the middle. I don't know why. It seems like 2 pi n would make more sense, but they usually write it 2n pi. Or 5 pi 6 plus 2n pi. Now, of course, n can be any integer. 0, then you would have pi 6 or 5 pi 6. Okay? 1 would be the next one over there, plus 2 pi. Minus 1 would be minus 2 pi. Plus, if n was 2, that would be plus 4 pi, or minus 4 pi. Yeah. So you see any integer, any integer. That lists them all, okay? And that's the general form for your solutions if they don't give you a limited domain. If they do give you a limited domain, then just list the ones within that domain. Okay. So here's how they write those. I did it ahead of time, but here it is. So x equal pi 6 plus 2n pi and 5 pi 6 plus 2n pi. That's your general solution, where n is any integer. You really probably should say n any integer. Most of the time I don't bother writing that, but it's understood. Any of you do any computer programming? Not yet. You might at some point. In the old days, okay, I'm not sure they still follow this rule, but it's a pretty good one. They let the variables n, m, and p, I think they left out o, but they sort of reserved those for integers, okay? Maybe they let L be 2. Any other variable, X, Y, Z, and stuff, any real number. Now, if they wanted to adjust that, they'd write that at the first of the program. Or sometimes some programs didn't do that, and you would do that. Tell the computer that n is this. So n is very commonly counted as an integer. That's why we sometimes don't say where n is any integer. Most of the time, if it's not going to be an integer, they'll say n is any real number, because you usually make the assumption n is going to be an integer. Not always, but that's just a little aside. Okay, so the figure below illustrates another way to show the equation sine x equal 1/2 has infinitely many solutions. If you do the unit circle, or any old circle here, and you show pi 6 here, then you know that's going to be 1/2 is going to be its value. The y value is 1/2. But it's also 1/2 over here, and that's a 5 pi 6, okay, because you're pi 6 short of your horizontal axis, which is the reference angle here is pi 6. And then you can see that anytime you go around the circle another 2 pi, you're at it again and again and again, or this one, or in this direction, again and again. 2 pi in either direction, you keep hitting that same point over and over and over. Okay? So any angles that are coterminal with pi 6 or 5 pi 6 will also be solutions for the equation. So when solving trigonometric equations, you should write your answer using the exact values rather than decimal approximations. Okay? I could tell when you went to radian mode, it came out decimal, and then you had to change it to get it to pi 6. It looked like you were doing that. Cody is here. I think this is who that is. Okay. Right. All right. Now, we're in just beginning 5.3. We're right now around page 362, getting ready to go to 363. And example 1's on 363. So here's an equation. Solve this equation. Sine x plus root 2 is equal to minus sine x. And I'll guarantee you that it's not an identity. That is an equation, a conditional equation. How would you go about solving? You tell me. Anybody? First step. If those didn't have signs in them, and it's just x plus root 2 is equal to minus x, what would be your first step? Yeah, all your x's together, and then later you'll get all the non-x's on the other side. So what would you do first here? Okay, add the one on the right to the left, okay? Sine x, so remember what we're doing is solving for the trig function. Later we'll try to figure out what the value of x is. So add sine x to both sides. What does that give you on the left-hand side now? Anybody? 2 sine x plus root 2, and these add to 0. So on the right-hand side you got a 0. Now what? Yeah, let's get the root 2 on the other side. Subtract root 2 from both sides. Okay, and this gives you 2 sine x that adds to 0 is equal to negative root 2. Okay, now what? Divide both sides. We were trying to isolate the trig function, so divide both sides by 2. Okay, that's out of there. Now we have a sine of x is equal to minus root 2 over 2. Now, what you got to figure out now is what values of x make that true. Now, first thing that I think of is where is sine negative? Is it negative in the first quadrant? No. Is it negative in the second quadrant? No. It's negative in the third and fourth quadrants. Okay? So your answer x is going to be something greater than pi, maybe 1 or 2 values greater than pi, but less than 2 pi, because once you get past 2 pi, it goes positive again. So that's where we're going to begin. They didn't give us any limitation on x, so we're going to assume all real numbers. So, now, that gives you what quadrant you're in. I don't know how you like to do this. I usually think in terms of reference angles. What reference angle will give you sine x equal root 2 over 2? What angle? Remember that one? Did I show you all this little trick? I don't know. I can't remember if I did or not. Okay. I'm going to draw a circle, pretending it's a circle, okay? And pretending it's a unit circle, okay? Now, this is angle 0, of course, okay? And then we have pi thirds, pi quarters, and pi 6, pi quarters, and pi thirds, okay? Now, here are the sine values. This is pi 6, pi fourths, pi thirds. And this is pi halves up here, so I'll put that one included in it too. Okay, the sine of 0 is 0. I'm going to put it 0 over 2, if that's okay. Yeah, I believe that's all right. Sine of pi 6, we just did, what's that? I'm actually going to put that the square root of 0 over 2. Okay? What is the sine of pi 6? We just did it a few minutes ago. 1 over 2. But I'm going to put it the square root of 1 over 2. That's still correct, isn't it? Okay. Next one. See, maybe a little pattern here. The square root of 2 over 2. The next one, the square root of 3 over 2. And this one up here is going to be the square root of 4 over 2. But what is the square root of 4? 2 and 2 over 2 is 1. That's how I remember, or one way I reinforce my memory of those of our favorite functions. 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Starting at 0. Square root of 0 over 2, square root of 1 over 2, square root of 2. Square root of 1 over 2 is 1/2. Square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2 is 1. Okay? So, all these anguished looks about, oh, what was that? You know, stuff. This may be easier to remember. Cosines step down and go the other way. At 90 degrees, or at pi halves, at 0, then 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2, which is 1. So you can use them both, but sine as you go, cosine is the reverse of that. Okay. I don't know if that's helpful or not, but it just seems like it takes y'all way too long to answer that pretty simple question. Okay. That may not be helpful at all. And maybe y'all just are very cautious. Okay. So, did we ever figure out what angle we're dealing with? Well, the pi fourths is our reference angle. In the third quadrant, what is the angle that has pi fourths as a reference angle? Anybody? Pi fourths beyond pi, so that would be, how many fourths is pi? That's 4/4 pi, right? So one more beyond that would be 5/4 pi. Or x equal, in the fourth quadrant, you're 1 or pi fourths short of 2 pi. So how many would that be? 7 pi fourths. But because we have no limitation here, sine has a period of 2 pi. So this will be plus 2n pi, and this will be plus 2n pi. Where n can be any integer. 0, you have those answers. 1, you have the next answer. -1, and the next answer this way. Okay? That's how you write the solution. Does that make sense? Pretty straightforward. Okay? Can I clear this? Whoops, I thought I had. Okay. And here's Dimitri. Okay. So let's see how they do it. Well, begin by isolating the sine x on one side of the equation or the other, so they just write the equation again. Well, isolate it. They added it to both sides, and that gave you 0 on the right and a 2 sine x on the left, plus root 2. Then subtract the root 2 from both sides, and keep the sine x as sine x plus sine x. For some reason, I don't know. That would be 2 sine x is equal to negative root 2. And then, next step, divide by 2. Okay, and you get sine x equal minus root 2 over 2. And at this point, you say, is this one of the angles I know? Yes, one that we know and love super well, because sine x has a period of 2 pi. Find all the solution first on the interval 0 to 2 pi. We did that, but we didn't say it that way. And that would be at 5/4 pi and 7/4 pi. How we got there was noticing the sign was negative. That had to be in the bottom 2 quadrants, third and fourth. And then its pi quarters would be your reference angle, so it's 5 quarters beyond pi and 5 pi quarters short of 2 pi. So there you have it. Then you add your 2n pi to both of those. There's your general solution, where n is any integer, which really should always be said. I usually just think it and not say it, but it should be there. Okay? Any questions? Exactly like we got. Okay, that was example 1, and they didn't do example 2. Shame on them. And by the way, there's a checkpoint after every example, so please do the checkpoints soon after class. Okay? So let's back up, and back up, and back up, back up, and let's do example 2 here. Solve this. 3 times tangent squared x minus 1 is equal to 0. What would you recommend doing with that? Second? Okay, you want to add 1 to both sides? Okay. And that gives you a 3 tangent squared x equal 1. What we're doing is isolating the trig function. Okay? We do that first by moving terms that don't contain them, or if they're on the other side that do contain them, over to the same side. And so we've done that, and what's next? Divide by 3 to further isolate the trig function, because now you got rid of the coefficient. However, that's tangent squared x. I really don't care what tangent squared x is. What do I need to know? Tangent x. So how do I get that? Take a square root of both sides, okay? So if I take a square root of this side, you get tangent x. Now, warning, warning, warning. Whenever you take square root of both sides of an equation, you've got to remember plus or minus. Got to remember that. So on this side, it's going to be plus or minus the square root of 1 over 3. Which, a little bit nicer way to write that is plus or minus, what's the square root of 1? Well, I'll do it this way. Square root of 1 over the square root of 3. That's the same thing. But what is the square root of 1? 1 over root 3. Now, if you don't like a radical in the denominator, you can do it one more step, and what does that be? Root 3 over 3. Okay, plus or minus root 3 over 3. Okay, that done. What in the world is your tangent then? What value x will give you either a plus or a minus root 3 over 3? Or 1 over root 3, whichever way you understand or see it best. Is there anything that seems to be familiar to you? What do you think? Second? Pi over 6, okay? Let's see. X equal pi 6. That would certainly, let's see, let's think about it. Tangent is sine over cosine, And tangent is, sine of pi 6 would be 1/2, and cosine would be, root 3 over 2, so that would be a 1 over root 3. Sure enough, that's it. The positive, anyway. Is there another place where tangent x would be either plus or minus root 3 over 3 or 1 over root 3? 1. That's pi 6 up from here.
5 pi over 6.
5 pi over 6, so let's try that one. Okay, now, yeah, okay. Now, for a different reason, but still true. Any others? Remember, it can be plus or minus. This one actually is a minus, because tangent is plus, minus, plus, minus. Okay. So the other one that would be plus would be beyond pi. Pi 6 beyond pi. Pi would be 6 pi, add 1, 7 pi. And whereas x equal 5 pi, it's negative in the second quadrant, it's also negative in the fourth quadrant, so that would be pi 6 short of 2 pi would be 11 pi. Okay, so x equal 11 pi over 6. Okay, sort of an ugly 11, but let's see if I can clean that up just a little bit. Okay, now, the next question is, what's the period for tangent? Pi, not 2 pi. So this would be plus n pi, and plus n pi, and plus n pi. Since they didn't give you an interval, you always assume this. So plus whatever your period is for that. Now the question I have to stop and ask myself, no, that would not include any of the others. Because these differ by 4 6 pi, these differ by 4 6 pi, or 2/3 pi. So yeah, they wouldn't be included. So this one actually has 4 different possibilities. 2 for the plus and 2 for the minus. And you did have plus or minus there. Okay. Let's see how the book did. Oh, wait a minute. Okay. Now, what's the difference between this one and that one? Notice this is a difference of 4 6 pi. This is a difference of 10 6 pi. I think that's something out. Am I missing something here? Oh, maybe this way. If you went around the other, no, that still wouldn't work. They're leaving out those two. This is where they're plus. And those are the only ones they list here. No, this is minus 2. Yeah, this is the minus 2. Plus and minus. But if you add, oh, okay, I'm sorry. Notice these differ by 6 pi 6. These differ by 6 pi 6. I'm looking at the wrong pairs. So you see this is redundant because these are replicated with those if you add in pi to it. So that's why they left them out. They were correct to do so. This is correct, but it's unnecessary because those angles are included by n pi. This is included by n pi. Because remember on the tangent, if this is this, the other one is exactly pi away from it. And this one, the other is exactly pi away from it. So, yeah, those were redundant. It's not wrong to put them, but it's just unnecessary. It's a waste of your time and effort. And be lazy. You don't want to waste time and effort. Okay. And there is a checkpoint there. All right. I think they leave off example 3 too, don't they? Yep. So let's do example 3. Any questions so far? Whoops. Goodness, my stomach's growling. Okay. Solve this. Cotangent x times cosine squared x is equal to 2 cotangent x. Okay. Excuse me, Stephanie's here. Does anyone else come in since I called roll? I missed seeing something. Okay. Whoa, here. What in the world can we do with this? That's an equation, not an identity, by the way. Second. Okay. Move the cotangent to the other side. Is that what you said? Or
I was thinking you just divide the cotangent out of the left side.
Ah, okay. Now that is a possibility. Okay? And what Jake said was divide both sides by cotangent x. Now that's okay, except for 2 things. Okay? One thing is that there are certain values where cotangent is not even defined. So I don't know how you divide by an undefined number. That's tricky. And the other is there some places where cotangent is 0. And by dividing both of those, you would be ignoring those values. Now, you will get an answer, and that answer will be a correct answer, but I think you'll miss some other correct answers. Okay? If that makes any sense. So what I would suggest is, like we did before, subtract 2 cotangent x from both sides. Okay? And that gives you cotangent x cosine squared x minus 2 cotangent x equal what? 0. Okay. Now what might you choose to do? Anybody? Factor. Okay. And what would you factor? It's the only common factor. Cotangent x times cosine squared x minus 2. And that's equal to 0. All right. Now we got 2 entities equal 0. See, at first it seemed like, whoa, we can't do this. We have 2 different trig functions in here. It's like having 2 variables in an equation. How can you do it? Well, if when you manipulate them, you can isolate them, yeah, it's okay to do. Okay? So this gives you either, what are your 2 options here? Cotangent x equals 0, which, notice that is an option for your solution here, whereas the way you are suggesting doing it, you'd be dividing by 0, and that wouldn't be you'd be losing these solutions. Okay? Or, what's the other option? Cosine squared x minus 2 is equal to 0. Okay? So what can you do with the first one? Where is cotangent equal to 0? Now you ask yourself, what is a cotangent anyway? In terms of your quotient identities or ratio identities. What is cotangent? Second? Okay, it's positive in the first and third quadrants. You're right there, absolutely. Okay, but I'm thinking, what is cotangent in terms of the quotient identities or ratio identities, whichever you want to call it? It's the reciprocal of tangent, that's for sure. But in terms of the quotient or the ratio identities, it's what? Cosine over sine. So anywhere cosine is 0, cotangent has to be 0, right? So that to me is easier to think of than cotangent. Where is cosine equal to 0? Where is cosine equal to 0? All of your half pi's. So this will be x equal pi halves, or I'm just going to write down 3 halves pi for now. Well, I don't even need that, do I? Because guess what? That's exactly pi away from pi halves. So that's just a multiple. So I think what we can easily write here is, since it's every half pi, this is x equal pi halves plus n pi, where n is any integer. Okay, so that's the left one. And see, we wouldn't have gotten these the other way because you'd been dividing by 0. Okay? So, what's the other possibility? What's the other possibility? That's for this 0. How about the other one? Second? Okay, in other words, you're saying cosine squared x is equal to 2. In other words, add 2 to both sides. Is that what you said to do? Okay. Now, where is that true? Second?
It's not going to work.
Not going to work at all. Why?
It's
outside of the domain, yeah, outside of the range of cosine. Because cosine is always between plus or minus 1, and there's no way you're going to square any of those numbers and get a 2. So this produces no solution. Okay. So we're just left with pi halves plus n pi. Okay, where n is any integer. Now, they did it with a graphing calculator and graphed the things and thought, oh my word, what a mess. But you see, it's only at the half pi's. Good deal. So that's a problem, dividing both sides of an equation by a variable or a function. Anything where that's equal to 0 could send things haywire and not give you an adequate solution. And, you know, there's other problems with that. So, anyway, go with that. Now I think we're ready for the next slide. Equations of the quadratic type, as if that last one didn't have a quadratic in it. But now many trigonometric equations are of the quadratic type, and they'll look a lot like this. Ax squared plus bx plus c is equal to 0. That's your standard form for a quadratic equation. And how would you go about solving that? Not these down here, but this. How would you go about solving that? Factor if you can, and if you can't, quadratic formula. Yeah. So, same thing if you have trig functions in here squared. Okay? So here's one in sine. 2 sine squared x minus sine x minus 1 is equal to 0. Here's one in secant. Secant squared x minus 3 secant x minus 2 is equal to 0. Here's a, this is just this written in a different way. That's written in a different way. So, we, again, solve for the trig function first. Pretend that's its own variable. okay, and say, well, what's the only possible factorization of 2 sine squared x? It's 2 sine x times sine x. What's the only possible well, you look at the sign of the last term, plus or minus, so we're going to have to try both of those, and then the only way you can factor 1 is 1 and 1. And then you try that, see if any of those factors will work. Same thing here. You see if any of this has to be secant x times secant x. This has to be plus or minus, and then either 1 or 2. So you try all those combinations to see if any of them will work. So to solve equations of this type, factor the quadratic, or when it is not possible, use the quadratic form. Okay, same as you would do for just x's in there. So here's one. Let's try it. And now it says find all solutions on the interval. So now we don't have to do the plus n pi's or 2 n pi's or whatever. So let's first do this. What might you try first? Hint, hint. Anybody? We're going right to it. Okay, how? 2 sine x times sine x. That's one of the only 2 possible ways to do it. The others put sine x in front. It doesn't really matter. But you have a possibility on your SIGN signs of the last term. This could either be a plus 1 or a minus 1. The other is either a minus 1 or a plus 1. Which goes where? Can you look that far ahead, or do you need to just try it trial and error? Plus and minus like this? Okay, and then what do you get? That has to be 1 and 1. The only possible factorization there. Let's FOIL it and see if we got it right. 2x times sine x is 2 sine squared x. 2 sine x times sine x is 2 sine squared x. Outer gives us minus 2 sine x. Inner gives us plus sine x. That's going to be a minus sine x. That checks. That checks. And this, of course, gives you minus 1. We are happy campers. Okay? Now, what do you do with that then? I'll go on and erase my smiley face here because I don't feel that happy. Okay. Where do you go from there? Yes, okay, 0 product principle. Either 2 sine x plus 1 is equal to 0, or sine x minus 1 is equal to 0. What do you do on the left? The first one. Okay. 2 sine x, what did you say again? Is equal to negative 1, is that what you said? Okay, and then divide by 2. Is that right? Okay, good deal. So sine x is equal to negative 1/2, if I could write. Okay, or sine x is equal to 1. Okay, let's deal with the first one first. Looks a little familiar, doesn't it? Where in the world is sine x equal to negative 1/2? Any thoughts on that? Where is sine x equal to negative 1/2? Second? 7 pi 6 is certainly one of them. Okay. Any others? Second? Anybody? 11 pi 6 was another one. And those are both between 0 and 2 pi, and those are the only 2 that will work there, so we're finished with those. How about this, where sine x is equal to 1? Oh, that's at x equal pi halves. And that's the only place between 0 and 2 pi where that will be true too. So we add this to the mix, and there are your 3 possible places where that quadratic solution will be true. Okay? Now, just in case this was bugging you, which I could tell it was just by your expressions on your face, you were really worried about this. Remember, a quadratic function, x's and stuff, have at most two solutions. But remember, this is a periodic function, so you can easily get more than two solutions, even from a quadratic there. Even if you limit the domain, because you had two within one period and one inside the period too. So don't get bent out of shape that you have more than two solutions, because periodic functions usually give you infinite number of solutions. So we're okay. Let's see how the book did it. All right, to erase. Okay, treat the equation as a quadratic in sign and factor. Okay, so 2 sine x plus 1 times sine x minus 1, just like y'all factored. Then you set each of those equal to 0. 2 sine x plus 1 equals 0. Or sine x minus 1 is equal to 0. That's gracious. First gives you sine x equal negative 1/2. The other gives you sine x equal 1. Sine x is negative 1/2 when x is 7/6 pi or 11/6 pi. It's equal to 1 only at pi halves between 0 and 2 pi. That's all she wrote, folks. Okay, so that's equation 4, or example 4. All right. They skip over to functions involving multiple angles. They still have another example here that I think we need to do. There's not much room on that page. I think that is the most room. All right. Example 5 says this. Solve this. 2 sine squared x plus 3 cosine x minus 3 is equal to 0. Any bells, whistles, flags, or other things happen here? Oh, you have different trig functions in there. I can't factor that with different trig functions in it. Okay? Now, earlier we had 2 with it, but we could move things around and then factor and separate them. These aren't separable, not by factorization. So what can we do? Yes, and which one would you choose that we use? Okay, and how does that go? Sine squared x, what do you say? Plus cosine squared x is equal to 1. That's certainly true everywhere, always. How do you use that here?
You can, with the Pythagorean one, you can subtract both sides by cosine x, making sine x, or sine squared x equal to 1 minus.
Okay, so I think I would solve for sine squared and do sine squared x is equal to 1 minus cosine squared x, because you're wanting to get everything in terms of cosine. You can't change the cosine to sine, but you can change the sine squared to cosine squared, and this is how you do it. So this will be 2 times 1 minus cosine squared x plus 3 cosine x minus 3 equals 0. Okay. Tends to make it look a little more complicated, but at least you got rid of the odd trig function. So what does this give you? 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Now what would you do? Say again?
Could you not add the 2 in front to the negative 3?
One more time.
Could you not add like terms?
Yes. Add the 2 to the minus 3, and what do you get? Negative 1. So I have a negative 2 cosine squared x plus 3 cosine x minus 1 equals 0. Combine like terms. Exactly. Somehow I changed that to minus, plus to minus. Didn't mean to. Okay? Now what? Second? I guess I could, but I don't want to. I don't like. What don't I like about that? Yeah, it's leading off with a negative. And since this is an equation is legal to multiply or divide by anything other than 0. Don't ever multiply by 0 or divide by 0. That wipes out all the meaning or makes it undefined. But you can multiply or divide by, say, a negative 1 and make this a plus, that a minus, and this last one a plus. I just multiplied or divided by negative 1. Now I like the looks of that a little bit better. Still don't know if I can do it or not, but let's see what we get. If it's factorable, we don't know if it is or not, but if it is, what would be the only possible first factors? Did I hear a 2 cosine x? You didn't. I didn't hear that. What did you say?
2 cosine x.
You did say that. Okay.
I just now said it.
Okay. 2 cosine x times cosine x. Did you say cosine x the first time? Oh, you did. Okay. Okay. Now, that's the only possible factorization of your first term. Where do we look next? The sign of the last term. What is that? Plus. What does that tell you these two signs have to be? Second? The same. And then you look at the middle term and see what that same should be. Both negative. You can't have both positive and it turn out being negative in the middle, so they both have to be negative. And then what's the only factorization for 1? 1 times 1. I don't know if this works. Let's see if it does. 2 cosine x times cosine x is 2 cosine squared x. That part works. This is minus 2 cosine x, minus cosine x, minus 3 cosine x. That part works. And then minus is plus 1. Yes, that works. So where do we go from here? So each of them equal to 0. So that's 2 cosine x minus 1 equals 0. Or I'm going to write the other one over here. Or cosine x minus 1 equals 0. Okay, what does the first give you? Anybody? Huh? Okay, 2 cosine x is equal to 1. And what does that give you? Cosine, divide both sides by 2. What he did here was add 1 to both sides. Okay? And then you divide it by 2. And what does that give you? Okay, cosine x equal 1/2. Okay? And the other one gives you cosine x equal 1. Now they didn't, oh yes, wait, let me see. This is example 5. They did not give you an interval, so you're going to have to do a general solution. What are some values for x that would make this true? Cosine x equal 1/2. Pi what? Pi over 3 would certainly work. Is that the only one? That's in the first quadrant. Cosine is positive. Where else is cosine positive? Fourth quadrant. Tangent positive is the third. Okay. Fourth quadrant. Okay. And what would be equivalent to pi thirds in the fourth quadrant? Not the same, but same reference rate. 5 pi over 3. Okay. So let me start writing these down. So x equal pi thirds. And what's the period for pi? For a cosine?
2 pi.
Plus 2n pi. So that's 1. X equal, you said 5 pi thirds plus 2n pi. And where is cosine x equal to 1?
0.
At 0. So let's just call that x equal n pi, 2n pi. Where n could be 0, 1, 2, 3, 7, yeah, anything in any energy. Those will be our possibilities. None of those are a multiple of your multiplier apart from each other. So let's see what they got. Cosine equal, x equal 2n pi. We did that last, they did it first. Pi thirds plus 2n pi, and then 5 pi thirds plus 2n pi. Good for them. They got it right. There is a checkpoint after every example. Please do those as soon as you can after class. I didn't pull out my... have I lost my watch? No, here it is. I have a broken pen. I'll never have gotten it fixed. How are we doing? We got a good 15 minutes or plus left to go, right? Good. Okay. All right, so that was example 5. I think we still have an example 6 that's not on the slide set, so let's do that one. I should have asked, I need to leave that up there a little longer. Sorry if I didn't. I hope I don't need to because it's gone. Okay, now this one happens to be one that you can see larsonprecalculus.com for an interactive version of this type of an example, so you might want to consider that. Find all the solutions of cosine x plus 1 is equal to sine x on the interval 0 to 2 pi. Uh-oh, SpaghettiOs. How in the world can we do that? Any ideas? Anybody? Give me something to work with. Where would you start?
So you can move trig functions by themselves.
Okay, now what do you mean by that?
Move the sine over, I guess,
Okay, a little louder.
move the sine to the left side and one to the right side.
Okay, oh, I see. Get all the trig functions on the left and then minus 1 on the right.
Yeah.
Is that what you mean? Is that going to help us a lot? Because then you have cosine x minus sine x is equal to minus 1. It's still a mess. Any other ideas? Good idea, but I don't think it gets you anywhere. What's the problem here? We don't have a trig identity that relates sines to cosines themselves, except for the, okay, and what are those involving?
Squares.
Squares. Neither one of these are squared. So what might we choose to do? Say again? Square both sides. Okay. Warning, warning. Anytime you do square both sides of an equation, you should still get solutions that work, but you may introduce what we call extraneous solutions that may not work. So we really should be checking every answer to make sure we got a correct answer, but on these you have to. Anytime you square both sides of an equation, you've got to check every solution to make sure it works in the original problem. So what is the left-hand side squared? Does anyone know? We're going to square both sides. All right, good deal. Oops, okay. All right, good deal. Thank you. Anyone know what that left-hand side will be? You can pull it off to the side and foil it if you want to, unless you happen to remember the little rule for doing that. Square. Huh?
Cosine squared x
Cosine squared x, I'll buy that.
plus 2 cosine
Plus 2 cosine x, very good,
plus 1.
plus 1. And that's equal to sine squared x. Now, did that help us any, or did that just make it worse? How?
The sine squared x.
Yes, now you can write sine squared in terms of cosine squared. Can't do it over here because you still have a cosine x there that we can't deal with, but you can do it with the sine. And what is sine squared? 1 minus cosine squared x. Okay, so we'll just take out the middleman here. Now what do we do? Yes, now we'll add a cosine squared x to both sides. Okay, and also, because this is a quadratic, we don't want to isolate. We want to get everything on one side, 0 on the other, so let's subtract 1 from both sides. Uh-oh, look what happens there. What do we get now? It's an ugly cosine. 2 cosine squared x plus 2 cosine x. Those add to 0. Those add to 0 equals 0. Wow. Now what would you do? Factor what out? 2 cosine x from both sides, because that's the greatest common factor. What are you left with? Anybody? Help me. Cosine x plus 1. Because you factored out the 2, right? That's equal to 0. Now what? Anybody? Always the next. Huh? Okay, yeah, it's factored, so set each of these equal to 0. So either 2 cosine x is equal to 0, because here you have 2 entities multiplied together give you 0. That means one or the other or both of them have to be 0. Or cosine x plus 1 equals 0. Now, where is 2 cosine x equal to 0? At your half pi's. All the half pi's in the interval 0 to 2 pi. So what would those be? X equal to, because you see you can divide out the 2 and it's gone. Divide by 2 and still 0, okay? So x equal pi halves, you said. Any others? And 3 halves pi. Okay. And that's all within 0 to 2 pi. I think I wrote that wrong too. Oh, I can't even find it. This is not a square bracket. That's a open parentheses. Okay. All right. Sorry. Okay, those are both within that domain. And they're the only 2 within that domain where cosine x is equal to 0. So what does the other one give you? Cosine x equal negative 1. And where is that true? At pi. So x equal pi. And that's the only place in the interval 0 to 2 pi where cosine x is negative 1. So there are 3 potential solutions. Are we through? Why not? We got to check them because we squared both sides of the equation. So let's go back to the original equation, which I adulterated here by squaring. So let's go back here. And let's see if these work. Okay? So let's try pi halves. What is cosine of pi halves? Anybody? 0. Plus 1 is? 1. And what's sine of pi halves? 1. 1 is equal to 1. I'm happy with that one. Okay? Now, 3 halves pi. What is cosine of 3 halves pi? Yep. 0 plus 1 is 1. What is sine of 3 halves pi? Negative 1. 1 is not equal to -1, not in this universe, so this one's out of there. Okay, how about pi? What's cosine of pi? Cosine of pi. Anybody? -1 plus 1 would be 0. And what's sine of pi? 0. 0 is equal to 0. I'll buy that one too. Okay. 2 of the 3 were correct solutions. 1 of them was not. Anytime you square both sides of an equation, you've got to check your results. You may have introduced extraneous solutions, and you don't want to do that. Okay. Now, how are we doing? Oh, we got a few more minutes. Let's move on to functions of multiple angles. Any questions so far? Okay. Functions involving multiple angles. What in the world do we mean by that? In the next example involves, that should be an S or either an S here or an S here. The next example involves, or the next examples involve one or the other. You got to have an S in one of those. Trig functions of multiple angles of the form cosine KU or tangent KU or something like that. Okay? To solve for these, now remember, if you had a regular variable, you just solve for the variable. If you have a trig function, you solve for the trig function first and then for the variable. If you have a multiple angle, you solve for the trig function first, then solve for your KU, and then solve for U. So it's a 3-step solution. I mean, there may be more steps involved in getting the solution, but once you have something, you have 2 more steps to go. So you first solve the equation for the trig function, then you solve it for KU, then you solve it for U by dividing by K. Okay? So here's one. Let's see what we can do with it. Do we have time? I think we do. Yeah, let's try it. What would you do first? Anybody? Anybody? Add 1 to both sides. Sounds like a winner to me. Okay? That gives you 2 cosine 3t. Now, the reason you do that, the cosine is to the first power. So you treat it like a plain x. These add to 0, and that's equal to 1. Now what? Divide by 2. That's pretty easy. So you have a cosine of 3t is equal to 1/2. Okay, we've done the first step, solve for the trig function. Okay? But now we have to solve not for t, but for 3t. What angle 3t would give you a cosine of 1/2? Answered this before. Pi-thirds. Okay? So 3t is equal to pi-thirds. But they didn't give us an interval here, so you have to include all the possibility, which would be plus, what's the period for cosine? 2 pi, so you do 2n pi. There you solve for 3t. But that's not what we're looking for. We're looking for the values of t. So what do? Divide everything by 3. Okay? So now you'll get t is equal to, this would now be pi-9ths plus 2/3 n pi. I like to do 2/3 pi n, but they do n pi, I think. All right, let's see what they got. T is, whoa! How did I botch it up? Oh, I didn't do enough of them, did I? That's one possibility. That's one place where cosine is 1/2. There is another one. 3t could be, where else is cosine positive? 5 pi-thirds, exactly. So this could be 5 pi over 3. But Wait. Yeah. Okay. But cosine is period of 2 pi, so we add our 2 n pi here. And again, we divide by 3, divide by 3, divide by 3, and you get t is equal to 5/9 pi plus 2/3 n pi. Okay. Yes. Or they put 2 n pi over 3. I don't care which way you put it. Okay? Does that make sense? All right. How are we doing? 5 minutes. Good. We got more time. Good. Let's see how they did it then. My watch is fast, so I never know exactly if I got the right timer. That's not what I wanted. I wanted to erase all those. Okay. So they started off by writing it again. A very good idea. Okay. Then they added 1 to both sides like we did. Then they divided by 2 like we did. And you get cosine of 3t is 1/2. So we know by that 3t has to be either pi thirds or 5 pi thirds. I forgot that one before. And then that's what 3t is. So then the next step is divide both sides of both equations by 3. And that would give you pi naught plus 2 n pi over 3, or 2/3 n pi, or however you want to say it. And the other one is t is equal to 5/9 pi plus 2 n pi over 3, where n is any. Okay. That confirmed what we did. Got the same answers. Okay, there is a checkpoint there. Please do it as soon as you can outside of class. Okay. Now, they're skipping the next one too. Do we have time for it? What do you think? 3 minutes. I have a feeling I might not be able to get that done in 3 minutes. So let's plan to start next time at example 8. I need to erase my earlier mark, because that was in another term. Okay? But we do have time for some homework exercises. I knew y'all wanted me to stop early so I could assign those. So here's possibilities. Do any of the odds 5 through 10 and 5 through 9? They're all at calcchat.com. Do any of the odds 11 through 27? They're all at calcchat.com. 13 is at calcview.com as well. Then do any of the odds 29 through 37? They're all at calcchat.com. 29 is at calcview. And then start working on 39 to 45. If you can't get all those, good deal, thank you so much. If you can't get all those, then, do what you can. They're all at CalcChat, 39's at CalcView. And we'll pick up the rest of those next time. Now, okay. Good deal. Have a good weekend. Of course, working on 3 will make it.
I got this last problem.
Okay.
The angle of depression. There's the 100-foot tower.
Okay.
And you look from the top of the tower, right?
Right.
40 feet from the base of the tower. So you're going to look down this way, right?
Angle of depression created from the top of the tower to a point 43 feet from the base. Yeah, yeah. Good deal.
But when you find the depression, you'll use the arc tangent instead of the normal.
Yeah, well, after you set up that gives you a trig function tangent, right? Okay.
Tangent of theta is 43.
Well, let's take a look at that. That's your angle of theta there. Okay. No. What's the angle of depression?
Because elevation would be from the top, right?
Yeah. Elevation elevation is from horizontal up,
Okay.
and depression is from horizontal down.
Yeah.
Not that.
It's not that.
No, that's not it. Okay. Yeah, technically, it's this from horizontal down. Okay. So that means. See, same triangle, but yeah. And the other way to look at it, your depression from the top down is the same as elevation.
Yeah.
You could use
That
one
one.
at the bottom.
I already know how to use mine. It's just scientific. Do you know Miss Martin's tutoring schedule?
It's just what Martin.
Yes.
I don't know it personally.
Okay, I can email her. I just didn't know if you
Yeah.
knew it.
You know where her office is?
Yes.
Okay, she probably has it posted on the door.
Her tutoring hours.
What's that?
Tutoring hours.
Well, you check the office hours and probably any of those would be okay. Or if not, she'll let you know.
I know she used to do it for the student support services. That's where I used to go see her.
Right.
Yeah. I saw her the first day when you weren't here, and I talked to her about it, but I haven't went to see her.
Yeah, you can check on her door or email her too. That would
I
work
will.
too. Yeah. All right, where did I leave off?